In this video we built a joystick mouse controller using STM32 ADC UART, Linux and Python. The schematic shows the complete electrical idea. The joystick is powered from 3.3 volts, not from 5 volts. VRX and VRI are analog outputs. They go to STM32 ADC inputs PA0 and PA1. The joystick button SW goes to PB0 as a digital input with internal pull-up enabled. Now we move from the schematic to the real hardware setup on the bench. Here the joystick module is connected on a breadboard and wired to the NUCLEO-G474RE board. The joystick supply pin is connected to 3.3 volts because the STM32 ADC input range is from 0 to 3.3 volts. VRX is connected to PA0, VRY is connected to PA1 and SW is connected to PB0. The STM32 reads analog joystick movement and sends the measured values to the computer. In the terminal we can see the serial data arriving through the ST-Link virtual COM port. The serial output contains X and Y ADC values plus SW for the push button state. When the joystick is centered, both ADC values stay near the middle of the 12-bit range. 12-bit ADC gives values from 0 to 4095, so the center is expected near 2048. In real life the center is not perfect. This joystick is centered around roughly 1980. The joystick is moved, the X and Y numbers change immediately in the terminal. That confirms that the analog voltages are being converted correctly by the STM32 ADC. The Python script reads the same serial stream and converts these numbers into mouse movement. Here is the desktop cursor is being controlled by the physical joystick. The joystick button is also used as a mouse click because SW changes when the stick is pressed. Before the Python part, the STM32 project must be configured correctly in STM32 CubeIDE mix. In Cube, PA0 is selected as ADC2 in 1 for the x-axis. PA1 is selected as ADC2 in 2 for the y-axis. Both ADC channels are configured as single-ended inputs, because the joystick outputs voltage is relative to the ground. ADC2 is configured with two regular conversions, one for X and one for Y. Rank 1 reads channel 1, which is PA0 and joystick VRX. Rank 2 reads channel 2, which is PA1 and joystick VRY. The sampling time is set longer because joystick potentiometer is slow and does not require fast sampling. PB0 is configured as a GPIO input with a pull-up for the joystick push button. With the pull-up enabled, not pressed means high and pressed means low. This is why the button is active low in both STM32 code and Python code. After the ADC and GPIO settings are ready, CubeMX chip generates the STM32 initialization code. Now we switch to STM32 CubeIDE and add the application logic in main.c. The code uses HAL ADC start to begin the ADC conversion sequence. HAL ADC poll for conversion waits until the ADC value is ready. HAL ADC get value reads the current conversion result from ADC2. Because there are two ranks, the function reads X first and then Y. After reading both values, HAL ADC stops the ADC until the next loop iteration. The button is read using HAL GPIO read pin on the button click pin. The firmware then prints X, Y and SW over UART using printf. The ST-Link virtual COM port carries this text to Linux as TTY ACM0. The serial format is intentionally simple: x equals value, y equals value, SW equals value. This makes it easy for Python to parse without writing a complicated protocol. Now the terminal shows the live stream from the STM32 board. When the joystick is moved, the ADC values change and the serial output updates continuously. When the joystick button is pressed, the SW becomes 0, which means button pressed. Now we open the Python script that turns serial data into real mouse control. The script uses PySerial to read from TTY ACM0 at 115.200 baud. It uses Py input to move the mouse cursor and press or release the left mouse button. The script stores measured center values for X and Y because the joystick center is not exactly 2048, and that's only set so the cursor does not shake when the joystick is close to the center. The speed multiplier controls how fast the cursor moves for a given joystick displacement. The regular expression extracts X, Y and SW from each line sent by STM32. After parsing, the script computes Tx and Ty by subtracting the joystick center values. Small Tx and Ty values are ignored by the dead zone function. The remaining values are multiplied by the speed factor and sent to mouse move. For the button, SW equals 0 means the joystick switch is pressed. When SW becomes 0, Python calls mouse press for the left button. When SW goes back to 1, Python calls mouse release. This prevents repeated clicks and gives normal press and release behavior. One important Linux detail: direct mouse movement may not work under Wayland. For this demo, switching to an XLR desktop session allows Py input to control the cursor. The final result is a complete embedded to PC control chain. Joystick voltage goes to STM32 ADC, STM32 sends UART data, and Python turns it into a mouse movement and clicks. Thanks for watching.